Aloha. Welcome on behalf of the UCLA Alumni Hawaii Network. Thank you for joining us and for your support of our scholarship fund through this event. To stay connected, you can find the UCLA Bruin Club of Hawaii on Facebook. For tonight's program, you'll hear from Devin Chu, a Keck All-sky Precision Adaptive Optics postdoctoral scholar at UCLA, followed by Professor Andrea Ghez, with an opportunity for Q&A following their presentations. Please submit questions for our speakers in the Q&A box. And now I'd like to introduce Associate Vice Chancellor of Alumni Affairs, Julie Sina, who will be moderating tonight's discussion.
Thank you so much, Christine. And I want to begin by thanking you for your leadership of our Bruins in Hawaii. And on behalf of 500,000 Bruins around the world, so thrilled to be with you tonight and look forward to many things. One is hopefully in the very near future, being able to visit with you in Hawaii, but also in the fall, hopefully welcoming you back to campus. And if you're able to join us in the Rose Bowl, we were just talking about our fall football season launch. So as Christine said, we're going to begin tonight. I have the thrill of welcoming Devin Chu to start us off. Devin actually grew up in Hilo and most recently received his Ph.D. in both astronomy and astrophysics from UCLA under the supervision of Professor Andrea Ghez and Tuan Do as a member of the UCLA Galactic Center Group. So Devin, welcome. And why don't you kick us off for tonight?
Mahalo, Julie, for that introduction. So aloha, everyone. It is my pleasure to speak to you all tonight. I think it's safe to say that growing up in Hawaii brings a great sense of pride, and it's always a joy to attend these events where we all share this connection to Hawaii. So as mentioned before, I grew up in Hilo, Hawaii on the Big Island, and I am a 5th generation Big Island boy. I really remember looking up at the night sky when it was clear, and albeit that wasn't very often in rainy Hilo town, but I remember like when I would look up at in the clear night sky and seeing the beautiful stars above. And I became interested in astronomy thanks to books from the Hilo Public Library and public outreach events that took place in our community. And I am so grateful for the sense of ohana that I felt growing up in Hilo. And thanks to such a supportive astronomy community, I was able to conduct my own science fair project in astronomy while as a student at Hilo Intermediate School. Little did I know that while looking through a Hawaii Department of Education telescope for my science fair project, my future PhD advisor and future Nobel Laureate, Dr. Andrea Ghez, was looking at data from the Keck telescopes located on my home island. And it's incredible to look back and see that groundbreaking science was taking place at the same time as my 8th grade science fair project. So fast forward to 2014, I was looking into graduate school programs in astronomy and astrophysics. At the time, I didn't know what type of science cases I wanted to study. I just knew that I wanted to conduct astronomical observations with telescopes. And when I spoke to Andrea for my graduate school visit, Andrea talked about the incredible opportunities to observe with the Keck telescopes to push our understanding of the universe. And Andrea's enthusiasm was a major reason why I decided to attend UCLA for graduate school. And working with Andrea and the Galactic Center Group as a graduate student was a tremendous experience. And immediately after joining the group, I and other graduate students were given parts of our incredible data set to analyze and maintain. And this really instilled a sense of ownership within me, knowing that I was contributing to the science goals of the Galactic Center Group. And the nature of our data set also meant that we were constantly working with fellow group members. And this structure established a sense of community, something that I really appreciated during my time as a graduate student. And Andrea believes that graduate students should learn how to conduct telescope observations. So I learned how to, drive the telescopes within my first year of graduate school. And I'm so grateful for these opportunities because it made me appreciate the data set that I worked with. And related to this, I had the opportunity to return to Hawaii Island to conduct the telescope's observations at the Keck Observatory. And for me, these observations were not just a work trip, they were an opportunity to come home and see my family. I just felt so proud and happy knowing that my work brought me home. And so I really want to thank Andrea for these incredible opportunities, and mahalo nui to Andrea for making me the scientist I am today and for giving this boy from Hilo a chance. And so I'm sure you will all enjoy her talk tonight. And thank you very much.
Thank you so much, Devin. And I know that we are all here to hear Andrea, so I'll make my introduction very quick and just a little personal. When I first came to UCLA, and I'll just say that's just maybe a year or two, several years ago, in my very first week here, I had the opportunity to attend the first lecture in what was a series of lectures by faculty in the physics division of the college. And it was Andrea. And in all my years in higher education, I've never seen or been a part of a lecture that was provided or given by a faculty member with so much joy and, as Devin just talked about, enthusiasm for what she does. The joy for the work, the joy for the research, the joy for teaching. And another piece of that was her sense of gratitude for being part of this UCLA family. It actually, I ended up leaving that lecture. The dean came up to me and he's like, Julie, are you okay? I said, I've never been so moved in the classroom by a teacher as I was that day by Andrea and the joy she had for what she does. So the day when she learned that she was awarded the Nobel Prize, only one of 4 women in physics and the only woman among faculty at UCLA, there was this incredible enthusiasm from her campus community, because just as Andrea lifts up the work, this community feels so lifted by her. And I know that you'll feel that tonight in the conversation with her. So we do have an opportunity for questions, so send the questions in, but I'd like to move forward with absolutely introducing the incredible Andrea Ghez. So thank you, Andrea, for being with us tonight.
Thank you, Julie, for that lovely introduction. Julie and I actually have multiple connections. I will share at the end our other connection. And thank you, Devin, for joining us this evening. It's a real pleasure to speak to the Hawaii Alumni Network because Hawaii plays such an important role in our research. I really consider the Keck telescopes, which are the largest telescopes in the world, behind me, they're co-owned by the University of California and Caltech. So I really consider these to be my laboratory. Now, let me just get my screen share going here. Keep going. What I was interested in joining the UCLA faculty was in developing new ways of using these telescopes to get the highest resolution, most detailed pictures that you can of our universe. And the specific reason I was interested in doing this was in order to understand black holes, in particular, to demonstrate that these objects really do exist in the universe. So there are 2 big picture perspectives on why one might want to look for a supermassive black hole. In other words, why is this an interesting question? This question of, is there a supermassive black hole at the center of our own galaxy? And from a pure physics perspective, we really want to understand whether or not these objects that defy our understanding of physics really do exist in the universe. And the reason they defy our understanding is that we have these two fields. One is general relativity, which is the study of things with lots of gravity. And black holes are certainly sources of strong gravity. In fact, the gravity is so strong that near these objects, the concept of space and time become commingled. So today, here on Earth, we think of space and time as separate things, but near a black hole, the gravity is so strong, they become intertwined. So that's the study of things with lots of gravity. And then there's the study of things that are very small, which is the study of quantum mechanics. And black holes are also incredibly small. In fact, they're infinitesimally small. These are objects that have no finite size. So in fact, if you think about density, which is mass divided by volume, density, because they have no size, density goes to infinity. And that's in physics known as a singularity. And it's effectively a big red arrow that says, you do not have your description of the physical world correct here. And that's simply because we don't know how to make the fields of quantum mechanics mixed together with the study of general relativity. So really, black holes represent the frontier or the boundary of our understanding of the physical world. There's also a second perspective on why looking for black holes, and in particular, the really big ones, and I'll get back to what I mean by that in a moment, exist. We think these things exist at the center of galaxies. And we think that they have a very important role in shaping or controlling the formation and evolution of galaxies, which are the basic building blocks of our universe. So we really want to understand what role these central black holes play in the formation and evolution of galaxies. Today, we really believe that these are the central engines of the formation and evolution of galaxies. So we want to understand how that feedback works. Okay, so let's understand a bit more about black holes. Black holes are objects whose pull of gravity is so intense that nothing can escape them, not even light, so you can't see them directly. In fact, there's a point of last return. So while we say that the black hole itself has no finite size, there is an abstract size that we can associate with it, and that's known as the Schwarzschild radius, or otherwise known as the event horizon, which has been popularized by Star Trek. So this event horizon is a really interesting point, because you can't get information across the Schwarzschild radius. So if you were to say you and a pal were wanting to explore what a black hole is, and you agreed that your pal would go in and do the direct experiment, and you would stay at home and watch. Once your pal crosses the Schwarzschild radius, you would not be able to communicate back, and that's a two-way street. It's a really important information divide. But it's also important because every object has a Schwarzschild radius associated with it, and it's the radius that, if you could shrink an object down to that scale, gravity would overcome all other known forces and force the object to become the infinitesimally small object known as the black hole. So you, your friend, your cell phone all have a Schwarzschild radius, and it simply scales with mass. The more massive the object, the larger the Schwarzschild radius is. But our objective here is to show that there's a supermassive black hole. At least that was our original intent of the program that I started 25 years ago. And so we needed to show that there was a lot of mass inside a very small region. So that's the goal of demonstrating the existence of a supermassive black hole. Now, there are two fundamental kinds of black holes that exist in the universe. And it's the supermassive black holes that I'm particularly interested in. The supermassive black holes are thought to exist at the center of galaxies. And the reason that people hypothesized their existence was observations of galaxies that emit tremendous amounts of energy emanating out from their center. So this is a picture of a galaxy. It's taken at radio wavelengths, so not what your eye detects, at very long wavelengths in the region where maybe your cell phone works. And what you see are these, the whole scale of the galaxy, which is roughly 100 million stars, or 100 billion stars rather, pardon me, is about this scale. And emanating out from the core are these jets, and they're moving incredibly fast. So we can figure out how much energy is contained in the jet, and that says that there has to be a very strong central engine. And similarly, there's light at the center that doesn't look like stars or gas. And so we believe that that comes from material just outside the event horizon that's moving very fast and therefore very hot. So it's what we're looking at here, in fact, are the dining habits of a massive black hole. Okay. Now, only about 10% of all galaxies have this exotic phenomena emanating out from it. In fact, I like to call these galaxies, which are officially known as active galactic nuclei, the prima donnas of the galaxy world, because they're kind of show-offs. But these galaxies led to the question, do all galaxies harbor these supermassive black holes at their centers? Black holes that are maybe 1 million to 1 billion times the mass of the sun. Now, this is a picture of our galaxy, of what our galaxy might look like if we could get outside and look back. Galaxies, for the most part, are flattened disk-like structures, so we're looking at it face on. Our sun, our solar system resides roughly halfway out of our own galaxy, the Milky Way. So as in an analog, it would be roughly here in one of these spiral arms. And that's in the outskirts of the galaxy where things are pretty calm and slow moving. So I like to say that this is like living in the suburbs of our galaxy. Where we believe the black hole is at the center, which is intense and extreme. It's like the urban hub of the galaxy. The density of stars goes up, things move at a much faster clip, and almost any way that you can describe the physical phenomena associated with the galaxy becomes more violent or extreme in this region. But it is in this region that we believe the supermassive black hole resides. In our own galaxy, we have an interesting perspective because we're looking towards the center through the plane of the galaxy. So this is a beautiful photograph taken from the side of Mauna Kea by Brad Lewis. And here you can see, hopefully, the plane of the galaxy. And from Hawaii, you can usually get great views of the plane of our galaxy, unlike Los Angeles directly. Here you see the white emission that is associated with the stars in the galaxy. And hopefully you'll also notice a lack of light in the center. And that comes not from the stars, but rather from the dust. And the dust is very much like the dust that causes smog in Los Angeles. The dust is very good at blocking light that has a wavelength that's about the size of the dust particle. So it turns out it's a very good blocker of a light that your eye detects, the optical or visual. So light emanating from the center of the galaxy at visual wavelengths, only 1 out of every 10 billion photons makes it to our eye. So it's basically invisible, which is why we see this dark lane in the middle of the galaxy. If you go to the near infrared, which is where all our work has been done, and roughly where your TV remote control works, 1 out of every 10 photons or light packets makes it to us. And here I just want to pause to comment. Actually, this is one of the reasons it's so exciting to work at UCLA is because there was a tremendous investment made when Keck was being built roughly 30 years ago into astronomers and astrophysicists who are interested in working and developing technology associated with infrared astronomy. So UCLA has now developed one of the best programs for infrared astronomy in the world. And infrared is very good at studying anything that's quite dusty. And that has mostly to do with star birth, star deaths, and in the case of studying the centers of galaxies, because there's so much dust in the way. So it's been a wonderful place to work for the last 26 years. Now, this project, which is focused on discovering the supermassive black hole and more recently using it as a laboratory, the key is to see the stars that are as close to the heart of the galaxy as possible. And their motion tells you what's inside their orbit. Now, this has been an interesting journey, and quite frankly, I wish I had kept a journal over the last 26 years. It's been quite an adventure on science, technology, and politics as well. This started off as a vision for a 3-year program. So at the time that I began this project, I couldn't possibly imagine doing it 25 years later. But at the time we proposed this, as only a 3-year project to measure the motions of stars, it was actually turned down. It was turned down because people didn't believe that the technology would work. And even if it did, we wouldn't see stars. And even if we did, we wouldn't see their motions. And their motions are the key to showing that there's a black hole. Each star tells you how much mass is inside its orbit. And if you measure only not the complete orbit, but just little line segments, the ensemble properties can tell you what's going on. So in fact, that was the beginning, unambitious. And then ultimately we understood that we could do complete orbits. So we did prevail in ultimately getting Keck time. This is why I came to UCLA, which is to get access to these phenomenal facilities that are located in Hawaii. These telescopes, even themselves, are breakthroughs. There were UC scientists came up with a new design for mirrors that allowed us to achieve much greater sizes. So telescopes are described by the size of the collecting mirror. So Keck, each one, in fact, there are 2 Kecks, as you can see. And to give you a sense of scale, hopefully you can notice that these are very large SUVs down here to give you a sense of scale. So large telescopes. So these telescopes have primary mirror that's composed of 36 hexagonal segments, and that was a really new and innovative idea for building big mirrors. And in fact, is now the basis of most large telescopes that are being built. So in the coming month, James Webb Space Telescope will be launched and operating, and that in space, and that uses the same architecture as a number of other telescopes that have been built. So this was really a radical new idea. With these new telescopes, you can do 2 things. So the original reason people wanted to build these larger telescopes is to see things that are very faint. But in fact, what I care mostly about is the second reason you want to build big telescopes, which is the ability to see fine detail, what's known as angular resolution. So the larger your telescope, the smaller the detail that one should be able to see. The comparison I like to make here is to the art technique of pointillism with paintings with dots. So as you go closer and closer to the painting, increases your ability to see the individual dots. And having a larger and larger telescope similarly increases your ability to see the details of the universe. So in this project, where the key is to see the stars that are at the heart of the galaxy, this is essential, your ability to see fine detail. Now, this second promise of large telescopes is challenging to achieve, and this and the challenge is the Earth's atmosphere. Great for us, it allows us to survive here on Earth, but it is a total headache for doing astronomical imaging of the universe. And this animation demonstrates the problem. If there were no atmosphere, you would be seeing 5 stars at the center of the galaxy, and each star would be the size of the smallest structures that are dancing around, and it would be rock solid. So these bug splat patterns that you're seeing moving around constantly are from the atmosphere that's continually changing. The analogy I like to make, actually there's 2 analogies that I like to make. One is, if you think about a river moving by and you're trying to look at a pebble at the bottom of the river is like the atmosphere. So because it's moving, it's really hard to see that pebble. The other analogy that one can make about the atmosphere is that it's like a circus funhouse mirror that makes things look distorted, except that mirror is constantly moving. Okay, so much of my career has been focused on how to overcome the blurring effects of the Earth's atmosphere. And there's been a lot of very clever techniques for doing so. I mean, obviously one way to solve the problem of the atmosphere is to get above the atmosphere. And that's what Hubble Space Telescope has done incredibly well for the last many years, and what James Webb Space Telescope will again do very well. The thing to keep in mind is that Keck is much larger in telescope diameter than either one of these telescopes. So if you think about Hubble, which is 2.4 meters in diameter, Keck is 10 meters, which is a factor of 4. And in fact, the science that we do the advantage of telescope diameter goes as the diameter to the 4th power. So that's 4 times 4 times 4 times 4. And that's more, basically more than a factor of 100. So it's really worth working towards figuring out how to overcome the blurring effects of the Earth's atmosphere. So there's been a huge, there's been many different stages of the technological development. In the early years, it was a simple matter of modifying existing telescope instrumentation to allow the instrument to read out more quickly and to have a scale that was much smaller so you could see the detail. So this is when this instrument was actually being taken out of the telescope for the very last time. These pictures of Keck are actually kind of hard to appreciate, but maybe let me try to give you a sense of scale. Up here is the primary mirror. So you can see the hexagonal segments, and there are 36 of them that make up the primary mirror. So I think the other thing that I wanted to comment about Keck and the extraordinary scientific power of this observatory is that they allow scientists, young scientists, to come in with new ideas about how to modify and adapt the instrumentation to do new science. So there's a lot of flexibility, and there's really a sense of community and integration between the scientific community within UC and Caltech and the technical staff that works at the observatory. So it's an amazing partnership that I think allows us to do much better science because of that really deep collaboration. Now, the more recent technology, which is not just modifying the hardware a little bit and then collecting short exposures and using a lot of computational, so we did a lot of programming to try to disentangle what the atmosphere does compared to what the science object really is, has been, so I'd say that's hardware simple, software complex. The next phase of the work, this was after the first 10 years, became a hardware complex. And in principle, software is simple, but of course, it's actually been more software complex than we had originally planned. But it's incredibly powerful. And this advance came because of a declassification of work done in the military. Turns out the military cares about looking up and down through the atmosphere as much as the astronomers do, and it did a lot of developing work on these problems of how do you take the blurring effects of the Earth's atmosphere out. So as our community began to catch up, the government decided, rather than investing in two communities, to declassify what had happened on the military side. Okay, so you're already seeing a couple of things going on in this animation. We're looking at the beam of light that's come through the telescope system, bounced off the primary and into this instrument bay. All the work of this technology, the key element of this technology is actually in the upper right corner. And you're going to see what happens in a minute. So this is a deformable mirror. So using that analogy of the Circus Funhouse mirror, what's coming in are what I like to call Pringle potato chips, which are the wave fronts that bounced off the Circus Funhouse mirror of the atmosphere. And what you want to do is have that deformable mirror, this powerful piece, to take the opposite shape or the conjugate shape to what the atmosphere has done, so that when the wave front bounces off this element, it becomes flat again. So you have pancakes rather than potato chips coming out, and it works incredibly well. And so it allows you to take much longer exposures for the first time and look at different wavelengths. So there's tremendous power in terms of the scientific reach compared to what we were doing for the first 10 years that has been achieved. And that's allowed us to do a lot more science. So it's been an amazing 25-year adventure of basically surfing an incredible wave of technological development. All of this technology depends on being able to see something bright in the sky, and there isn't something bright in the sky anywhere, any arbitrary place you look. So part of this has been to use lasers. So these are lasers that shine up to a very thin layer of sodium atoms up in the atmosphere, up at 90 kilometers. It's just a fluke of nature that we're taking advantage of. It's meteorites that come down, they shed some sodium atoms that get trapped in this really small layer. And then we shine a laser and stimulate those atoms to shine and make a bright star wherever we want to look. And so this is a picture that I just love. It's a night that we had time on both Keck telescopes. Devin was controlling one side, and we had another team on the other side. And we can think of these lasers as giant laser pointers telling us where the center of the galaxy is. But really, it's just two adaptive optic systems working on these two telescopes so that we get these clean pictures. We just happen to have the same night. Now, this animation gives you a sense of what's happened. So if we take a long exposure, you see those 5 bright stars, they're blurred. So those were the bug splat patterns, but integrated over a longer time. And then these techniques allow us to see what's going on. And the key, remember, we want to see the stars that are as close to the center of the galaxy as possible. So it's the stars that are, so actually we see today, we track an area that's much larger than even this. So there's thousands of stars that we've discovered and have been tracking for the last 25 years. So if you have good names for stars, we are naming lots of them. And you're about to see some of my favorites. So you can see that where we want to focus our attention is inside this box, and this is where we think the black hole might reside. And in the next animation I'm going to show you is a fourth of the real estate of this little inset box. And you can see without doing these techniques, either the early ones or the later ones, you wouldn't be able to see any stars. So it gives me great pleasure actually just to show you these animations, these depictions of our data. Because remember, there was great skepticism that this would work and for a 3-year experiment. And here you can see that we've been going for far longer than anyone would have expected, because it just outperformed anything that we could possibly imagine when we got going. Now, let me just say there are 2 kinds of data sets that we take. One is the easiest. The first one is easy to explain. It's just images, and we're really used to taking pictures. So this is like, take a picture 1 year and you go back and you take you take another, a couple few, and those are easy. And then you put them together and you make a movie. So those are the ones that are easy to explain. And if you've been detected, if the star has been detected in an image, it's followed with a dotted line. So the fact that stars pop up in the middle of this is not because they become brighter, but rather because our technology lets us see fainter stars. Now, the more complicated kind of data is the kind of data, are the kind of data sets that Devin works on, which are spectroscopic data sets, which breaks up the stars into their separate wavelengths and allows us to measure how things are moving along the line of sight. So the images gets you 2 dimensions in the plane of the sky, and the spectra gives you the motion along your line of sight. And it's a technique that was only possible with the advent of adaptive optics. And once we can take a spectrum of a star, you're followed by a solid line. And this is important because you can probably tell what's my favorite star in the in the galaxy and probably in the universe. Its name is, well, at the moment, its name is SO2. And so it probably needs a better name. But it's incredibly powerful because the motion of this object is what tells us that there's 4 million times the mass of the sun inside a region that corresponds to the scale of our solar system. And that's an incredible advance. Before this project started, we knew that there was 4 million times the mass of the sun inside an enormous region. And what this experiment has done has to confine that mass to a region that's a factor of 10 million times smaller. So that's advanced our understanding or our evidence for the existence of a supermassive black hole by a factor of 10 million, moving the concept of supermassive black holes from a possibility to a certainty. I mean, just think about anything you could increase. This is a huge increase, a factor of 10 million. And in fact, the first experiment that we proposed for 3 years got us the first factor of 1,000. And then it worked so well that, and we realized that we could measure more than just motions on the plane of the sky, which would allow us to do a statistical estimate, but individual stars' motions got us the next factor of 10,000. So it's been a really interesting program in terms of this progression of increasing technology, increasing patience, because the duration of your data set also helps you a tremendous amount. But now we have the strongest evidence for the existence of a supermassive black hole in our galaxy, and not only in our galaxy, but any galaxy in the universe. So today, our objectives are no longer to prove the existence of a supermassive black hole, but rather to turn the black hole, or the center of the galaxy rather, into a laboratory for understanding the physics and the astrophysics of black holes. And one of the most delightful parts of this work is almost every prediction we could make for what we thought we should see at the center of the galaxy has been inconsistent with the observations. And I must apologize, this is another animation that has decided not to play. It's an enormous animation. So this is just this is a problem on my end. But I can talk through a few things that are very evident even in the still piece. There are three wonderful mysteries that have emerged that are depicted here. One prediction is that you shouldn't see young stars at the center of the galaxy. Young stars have just recently formed, and they form out of very fragile balls of gas and dust. And black holes have the tendency to pull things apart. In fact, we call this spaghettification. So black holes pull much more strongly on one end. So if you think about your friend, remember we sent your friend into the black hole. If your friend fell in feet first, the black hole would pull much more strongly on that person's feet than their head, and that person would become stretched apart, elongated or spaghettified, and would ultimately be completely torn apart by the black hole. So the anticipation is that you shouldn't be able to form young stars near a supermassive black hole. In fact, that was used as an argument against the possibility of the existence of a supermassive black hole at the center of the galaxy, was observations of young stars that were much further away. Now we have exquisite observations for a black hole, and yet the dominant kinds of stars that we see are young. Those are the blue-green stars that we see in this image. They dominate the kind of stars that we see. So I call that the paradox of youth. How do we form these young stars? And that's been quite a puzzle. Paradox number two is that the old stars, there should be tons of old stars around the black hole. And the reason that there should be tons of old stars is, well, they've had lots of time. With time, stars at large distances should be able to migrate in towards the center of the galaxy. In other words, there's a tendency to gravitate towards the most massive object in the system, which is the supermassive black hole. So the anticipation is there should be a cluster, an entourage of old things, and yet those are the orange things, and there are very few of them. So there's a dearth of old stars. So this is a puzzle and really important because we use that model for finding old black holes in other galaxies. And my last, but not least, but my favorite actually, recent paradoxes are these magenta things, which are actually objects that are being tidally torn apart as they pass through by the black hole. And we think that they may be formed by processes that may give us hints to what's driving the gravitational wave detections that have been recently discovered by LIGO. So I don't want to go into any of these in too much more detail because I'm running out of time. So in fact, I'm going to skip over all of this and just leave you with a thought that we are now advancing the next generation of adaptive optics to allow us to see more clearly with today's telescopes. And this is an important technological development for the advancement of the next generation of telescopes, such as the 30-meter telescope that's planned for the summit of Mauna Kea. But this is also a collaboration between all the next generation of telescope players, the TMT, the Giant Magellan Telescope, GMT, and the European Extremely Large Telescopes. These are very ambitious, but incredibly exciting projects, which will revolutionize our understanding of many objects, but of course, my favorite being the center of our galaxy. Today, we're just seeing the tip of the iceberg. And so being able to see deeper is incredibly important to our ability to solve these various paradoxes of how the supermassive black hole interacts with its environment. And for us to be able to probe what appears to be the presence of dark matter at the center of our galaxy. So with that, let me give lots of credit to the team. I started this project with two UCLA faculty, Mark Morris and Eric Becklin, when I first joined. And this is my very first grad student, so we were a very small team. And today we're a much larger team collaboration. You can see here, Devin, we're a core collaboration of 30, and we have a broader international collaboration or partnership of about 100 scientists today. So thank you so much for joining us this evening. I hope you've enjoyed this quick overview of all the work that's going on Mauna Kea. And I hope the next time we're over in Hawaii, you'll come out to see us. Thank you for your attention.
Thank you so much, Andrea. And hopefully all of our viewers and our Bruins in Hawaii can appreciate, just as Devin started out by talking about the enthusiasm with which you teach. So thank you for being with us. So there are a number of questions that have come in, but I'd like to start with this one. I'm just curious, when you go out at night and you look up in the sky, can you ever relax, or is that like work mode for you?
No, actually, it's not work mode, because work mode is sitting in front of a computer. We see the sky through a computer screen, and I think that's very fortunate, because it never takes the sense of romance when one goes out and sees a really beautiful dark sky. I have to say that's one of my favorite things about being able to go out to Hawaii, is the ability to see just a spectacular view with your own eyes. Yeah, it's both humbling and inspiring.
Thank you for that. When speaking of stars, somebody has already asked, getting back to what you suggested, how could one name a star?
Send us a suggestion.
People are taking you seriously, Andrea.
What?
People are taking that seriously. They're ready to name the stars.
Okay, excellent. Well, I mean, there's two ways. I mean, we really, if you really want your name, your star name, we have the Star Society program, which you're welcome to join, and we officially name stars after you, but you can always unofficially name any star you'd like.
Thank you. And Amber, you're welcome to put some information about that in the chat room if you would like. So switching gears a bit, question for both you and for Devin is, there's a number of questions about people are curious about how you're adjusting in COVID in terms of how that has impacted your research and the work that you do.
It's a great question. I'm really grateful for technology. Our work is very seasonal. And the reason it's seasonal is because the Earth goes around the sun. So our view of the center of the galaxy has an annual cycle. We need to be looking at the center of the galaxy when the Earth is between the center of the galaxy and the sun. So there's roughly a 6-month period that goes from the spring to the early fall that we're looking at the center of the galaxy. So last spring, of course, was the beginning of COVID. So all observatories all around the world were shut down. So that meant not happily, but it's not that we understand. So we lost a few months, but great. I'm really grateful for the observatories' efforts to figure out how to enable us to work from home. Mm-hmm. So we now not only do meetings, as Devin knows, we do a lot of meetings. So we meet quite regularly at different scales. So we try to bring our collaboration as a whole together once or twice a week, and then we have small scale projects. So I'd have to say the group has worked incredibly well under these conditions in the sense that we can log in to our computers at UCLA, but it's also been a really interesting opportunity for us to understand some of the challenges of our growing collaboration. So we started this project as UCLA only. All the data resides at UCLA, but we now have collaborations with people in Paris and Spain, Granada, Spain, or even more locally, Berkeley. But they faced some interesting challenges of getting in, and now we were all on the outside. So it's been an interesting moment for us to think about and work on some of those. I mean, it's forced us to think much, because we're now all on the outside, to become much better about issues of data accessibility. So, there's always some, like I say with the research, for every pro, there's a con. And of course, the con is that we're not talking to each other. But I'd say, given the conditions, we're working about as well as we can.
Devin, anything you want to add to that?
I think Andrea summed it up pretty well. Maybe the only thing I'd add is I'm very grateful that we have been able to, again, meet remotely and discuss things over the computer through Zoom. But there's also nothing that quite beats being able to just pop into someone's office and say, hey, I have a quick question, can you help me with this? And I felt that was very crucial. And so that is something that I do miss, but I understand the necessity of why that's not possible at the moment. But that is something I'm very much looking forward to once we're on the other side of this.
And I know we also all talk about Zoom fatigue, which, I think we all get that, but even in the midst of that, I'm still grateful to have this space together, but there's nothing like those informal conversations, like you said, Devin. Another question for you, Andrea, is, one thing that I'm not sure everybody is aware of is that you also still teach an intro class to astronomy, right? So what has the teaching been like for you, particularly for that undergraduate group during the COVID time?
Well, I think we're all figuring it out. So it's teaching by Zoom. For the last 10 years or so, I teach what I call my favorite class to teach at UCLA. I feel very lucky to teach it. It's an introductory to astronomy and astrophysics class for majors. It's grown quite a bit to this year. So, the major of astrophysics is quite small. It's about 50 students. So we teach by Zoom, and I think we're all getting a little smarter about how we do this. And there have been some elements of this in terms of how we do office hours that have worked quite well. So one of the things I like to do when we're in 3D is to run a study group in a conference room in the new physics and astronomy building. So if you haven't been by campus recently, come check out our lovely new digs. But it's a big room and there's a lot of noise. And the great thing about Zoom is you can do breakout rooms. So we do one breakout room problem so students can meet, because that's one thing I like to do with this class, is to try to set up a community, to have these students who are entering the major get to know each other, develop a community, learn to work with each other, and learn about the department. So it's given that we're forced to this mode, but I think there's nothing that beats being in the classroom. I think it's really important that we get back in the classroom. And something that I've becoming more and more, it's become more and more apparent, is that the level of cheating just across the nation has just gone through the roof. So while it's been an interesting look into what it means to be remote. So it's very popular to talk about the benefits of remote teaching, but I would also say that, I don't think it promotes integrity. So I'd like to see those students back in the classrooms, and I'd like to be able to develop those personal relationships, which are just so much harder to develop online.
Was those informal conversations again, Devin, that you were mentioning? Somebody asked about COVID a minute ago, but one of our listeners is curious about how your research and your work's been impacted since the Nobel Prize.
Yeah. Well, gosh, I'd say the Nobel Prize is it's interesting because there are many new opportunities and responsibilities that come with it. And so it's like many things in life, it's been that are disruptive. It's a wonderful opportunity to just take a moment and think about where is it that you really want to go. And I think what I've come to the conclusion is, the work is so exciting right now. I often get the comment, well, you're done. And I keep thinking, gosh, no. I do this because I like science, not because I wanted a prize.
So how do you answer that question? Where do you see yourself going at this point?
I really am excited about the future, and in particular about the advances that can be made with these large telescopes. And I think there's an incredible need for leadership with respect to the big telescopes. I think we're in we have a need for people who can play the role of being champions of discovery, who can speak about the science, and who are willing to engage in dialogue about what makes these projects hard. So I guess that's what I want to see. I want to contribute to those things becoming a reality.
Well, and one of the things I think has already been highlighted that you do that you certainly appreciate is also being cognizant of your legacy. encouraging students like Devin, teaching intro classes, and doing all of those things that keep all those conversations going. So a question, a little bit of getting back to your research that actually came from Christine is, any hints as to what the next paradox within our supermassive black hole may be?
Yes, actually,
I know that's a question you can answer in 10 minutes. I know.
Yes, I got an answer. But before we go back, I just wanted to comment. I mean, Julie, you phrased that so nicely, and I couldn't agree more with you about the just the benefits of doing research in a university context, that you're not only creating new knowledge by your scientific work, but you're also training the next generation of scientists. You're creating new knowledge in this other dimension, and working with students who constantly are asking you questions because they're trying to figure it out forces you to think really deeply about what you're doing. I have to say, it's one of the real joys of doing of being a professor in a university context. Okay, so new paradoxes. All right, well, let's focus on there's tons. Let's focus on Devin's. So let's see. Devin looks at binary stars. Most stars form as binary stars, it turns out. It's very poetic. They form with companions or twins out where the solar system is. But where Devin's looked, near the black hole, he hasn't found any. And given our basic understanding of how stars form, there should have been way more. So, where did all these companions go? And so I think that's a really interesting and important mystery to solve in terms of how the black hole interacts with its environment. So I think there's an important clue there. So that's one of my faves.
Devin, anything you want to add to that?
No, I think Andrea can sum it up pretty well, but that's what's really great is there's just so many interesting questions definitely in this region, and it's like really great to work with all our different collaborators. There's so many different questions, and so to tackle those questions, it helps to have a lot of people on them. So yeah, as Andrea mentioned, I'm really interested in binary stars and why there aren't any so close right now. But that's just definitely one of the many questions that we have. But yeah, since that's my most science focus, I'm personally most interested in that. Yeah.
Thank you so much for sharing that, Devin. So again, going a little bit different, we have a couple of folks that are wondering if civilians ever have access to the Keck telescope and that experience.
So under normal times, yes. So there are a couple of routes to get up there. So our Star Society program brings a group up once a year when we come out. So Amber can share with you how to join us the next time we go, which I'm hoping will be next summer. I suspect this summer we'll have to take another pass. And that's really because the summit of Mauna Kea is closed to all tours, as far as I can tell. There are wonderful tours that that take you up to the top. Just the tour companies. Maybe Devin knows, can remember some of the names off the top of his head. I'm blanking right now, but
we could probably get some of that information out to our viewers also. Maybe Devin will connect with you later about that. So how about one last question for both of you? As you think about your research in the future, what gives you the most hope?
Devin, you want to go?
Oh, that's a good question. Andrea, if you happen to have an answer, feel free to start off. Maybe get some thoughts together. But
the students actually give me hope. There's just endless and curiosity and drive to learn more. So it's I think that's again part of the great inspiration of doing research at a university.
yeah, I think to piggyback off what Andrea said, that's a great point. I've had, thanks to Andrea and the group, I've had opportunities to come back to Hawaii also to do educational outreach experiences and to get back to the community in that way. And like Andrea said, what's amazing is just seeing the enthusiasm of the students. And usually the students I'm working with are in high school or elementary ages, and they're just so excited, and it's just so great to see. And just seeing them so motivated and so excited about just science and being interested is like really great. And it just gives me hope that a lot of people are just really interested, and whether they stay in astronomy or not, it's just great to see them so excited. And I just truly feel as long as we give them the opportunity to succeed, that's what we can, I think that's like our responsibility. I think then it's for them to take advantage of it. But based on just their excitement, enthusiasm, it's just so hopeful.
Mhm. Well, you two certainly have demonstrated that for us tonight. So as we bring this evening to a close, I know we could go on much longer. I just really want to thank both of you, Bruins, supporting the Bruin community. Christine, thank you again for creating the opportunity and your leadership of our Bruins in Hawaii. And I think every time I look into the stars, Andrea, I think about you and the work that you're doing, and that gives me all the hope that I need. So thank you so very much. Hopefully everybody has a great rest of the evening, and go Bruins.